All right, so if I'm going to find area of this region, then I want to be able to interpret the double integral. Let's just say that the area is the double integral over d. D is the region inside. Okay, so double area over d of 1 dA. I need to be able to switch this to a line integral, and I've got to use the right function. And this is the part that people don't like, is you actually have to make a choice. There's lots of choices that you can pick for your function. I'm just going to use this one. Let's just use the very first one. So we're going to go ahead and say, well, look, this is the same thing as the integral along C of f dot dr with f equal to 0x. And why is this equal? This is equal exactly by Green's theorem, and the fact that if you want to check for f, you can check that q partial x minus p partial y is in fact 1. So we've switched this thing now using Green's theorem, and now we can, let's just go down here and we can write this as the integral from, well, I've got my parameterization for c, and so we said pi was going, t is going from 0 to 2 pi. So I've got my integral 0 to 2 pi. What do? I take my parameterization r of t and I plug it into my f. So I like the first component, 0, no problem. And then you just plug in what? Cosine of t for x. Boy, that worked out nice. Okay, so there's your f of r of t. Then you have to dot with r prime. Ooh, not so nice. We're going to get what? Minus sine of t. And then we're going to get comma derivative, so 3 sine squared t times the derivative of sine is cosine t dt. Let's clean this up a little bit, and we're going to get the integral from 0 to 2 pi of, let's see, 0 dot just kills that. So we're going to get a 3 out front, and we're going to have a, I'll just write the cosine first, a cosine squared sine squared t dt. And some of you are looking at this thing, okay, can't we just do it the other way? Can't we just view it as a double integral? Well, actually, it'd be pretty hard to, because you don't have a nice formula. I've not been able to solve for this region D as a formula where I can say, if I want to cut it as type 1, I want to go from the bottom curve to the top curve. Can't really do that when it's given by this parametric curve here. So we've got to work this one out. We're close. We just have to work out this integral. And let's just think how one does these. You saw these in Calc 2. And the idea is you want to use, I would switch, personally, I would switch the sine squared to 1 minus cosine squared, and then use the angle reduction formulas. There's another way you could do this one as well if you wanted to. Maybe I'll show you this way because I think it might be easier. But do you remember that sine of 2t is 2 sine t cosine t? So when you see a sine squared cosine squared, I can think about this as I'll need a 4 outside. So I'm going to put 3/4 0 to 2 pi. I can rewrite this as 2 sine t cosine t all squared dt. Check my work here. The 4's cancel. Yeah, it's the same. I haven't changed anything. And now I can write this as 3/4 0 to 2 pi. And I'm going to write this as sine of 2t all squared dt. Now you'll angle reduce this one time, and you're going to end up with 3/4 times pi, so 3 pi over 4th. Or again, you could have switched everything to sine or cosine. I usually go to cosines, so I'd switch the sine squared to a 1 minus cosine squared, and then angle reduce twice on that. I think this technique was easier. Either way, you're going to get to 3 pi fourths, and so that's pretty cool. We're able to get the area of this region, which you could not evaluate directly as a double integral. We were able to switch it though to a line integral and use Green's theorem. So we'll end this video here. I'll do one more example with you, and then I want to show you something interesting if we have time.